Go. What does it mean to be? Actually, the easiest way, if you have a function and you say it's continuous, if you can draw that function without lifting your pencil off the paper, that's an easy way to say something's continuous. Something that's not continuous, probably think of rational functions right away. Okay, in other words, they actually have jumps, they might have gaps. You can have functions like you can have a machine that turns off for a while and then it turns back on. So what it means to be continuous is that you have no holes in the function at all. All right, so let's make that where you can see it all. All right, so the height of a ball thrown straight up. And this is the type of stuff, not throwing a ball, of course, but you guys are going to deal with collecting data. So you're going to have some kind of experiment going on where you've collected data points here. If I take this data and I plot it, is this continuous? No. It's dots. It's discrete, exactly. But what we build is we say, well, I can make it, we can make it continuous. And the reason is if we see these dots going like this, we can assume that this function's not doing something like this, okay? I mean, it'd be very oddball if it did. And so we like to fill in those gaps and say, well, now it is a continuous function. There is a lot in engineering calculus that we like to have continuous functions, so we force them to be continuous just because there's a lot of theorems to use for them. All right, so I went ahead and I gave you this, okay? I think almost all of you will have to take biostats, and I know we talked about you had stats. If you don't have to take stats, I would take it. I think it's best class. Well, I just say that because that's what my degree's actually in. One second. And what I like about stats is when you're late, is when you're given data, I always say, well, where'd that come from? Where did they get this function? And you say, well, logically it makes sense because it's a negative quadratic and it'd be upside down, but how did they get that function? That's what statistics teaches you how to do, how to model data. And when you model data in math means you take data and you come up with an equation. Yeah, Justin?
Is there a difference between biostat and basic stats?
Probably it's going to be the same like this and in engineering calculus. I wouldn't say it would be that drastic of a difference, meaning like, is one harder than the other. I think in biostats you will just study more biology examples. Like in here, we'll have more biology examples.
And how come we can't get credit we got for stats?
For this?
Yeah, apparently they don't transfer credit.
I don't know.
That's silly.
Because you majored in biology. That's your problem, right? All right, so a function, and I get rid of all that discrete, and I make this completely smooth, then what's nice with a function, I, of course, can predict any one of these points, and I can get the in-between. And so the idea of a limit, and again, I'm going to be very vague. I'm not going to go into real details about this, is when you have a function, you can have a function that has, let's say, a hole in it right there, and then it goes off and does something else. Maybe it's this function's increasing, somebody turned the power off, it has to cool down and then warm back up. A limit says as I get very close to a particular point, so say in this case, as my x value gets close to 0, what's happening to the y? In algebra or pre-cal, you would say, well, that value doesn't exist because there's a hole there. The difference between a limit and a value, so a value of a function would be like, what's f of x, or in this case, f of 0. And we would say, well, that doesn't exist. There's a hole there. A limit says, I don't care what the value of the function is. As I'm getting really, 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 really close to it, what is this value going to? Well, this really, really, really close to it is that h value that you guys kept saying, well, what do I use if they don't give me h? 0.001? Well, again, in the real world, it depends on what you're doing, okay? And here, we just say really, really, really close, okay? Wiley, of course, would give you values, that you would use. On a test, I would give you values as well. But that's the big difference with a limit. A limit doesn't care what's happening at that exact point. It cares what's happening near it. And so we can get values, we can we can make a function like this continuous. Kind of funny to say, well, just get a crayon and, you know, color in the little hole there. You're late too. And but what we're doing here is we are assuming that this is continuous by filling this in, and now we can actually say, let's just say this value is 1, that the limit and the value of the function are equal, which means it is now continuous, okay? So limit this whole formula that you've been using, that f of x plus h minus f of x over h, that you've been using is the formula for a derivative. The difference is when we first started this class, seems like 10 years ago, doesn't it sometimes? Or is it that just for me? I feel like I've seen y'all for so long. All right, so we started this class and I said, slope, slope, slope. That's all you're doing is you're finding slopes. And we said, well, we're going to now make this look a little different and do something like this, okay? And that we called our average rate of change, which is still the slope. Well, then we said, well, if we want the instantaneous rate of change, what you did is you stuck the limit as h approaches 0 just in front of this definition. So guess what? You're still finding, thank you, you're still finding the slope. You're not doing anything different, and the slope is the derivative. The only thing different here is we're saying now, let this get very, 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 very small, because maybe we can't plug in the 0. Okay, once again, the value may not be equal there. And to a point where I can find out what is happening at an exact, you know, moment of time. Where this is between 1 and 3 seconds is good enough. This is no, I need to know at exactly 1 second what's going on. So this is what you have been doing limits already. It may not, you know, you may not have, I don't want to say you may not have known what you're doing, right? But I mean, that's what you've been doing when you say let h get really, really small, 0.01, 0.001. What are you doing? You're letting this value go to 0, and that's finding a limit, which saying I'm getting as close to the value that I want. It just so happens the value of our function is the slope function. So we're getting close to the value of. All right, so I find this, I use this in my engineering class, I find this the best example of understanding what a limit is. That a limit, you're getting very, very close to a value, but you're not reaching it exactly because you just can't. The world doesn't work perfectly that way. I think of my husband every time of this, and we make the, yeah, we're lazy, and we make the boxed potatoes, okay, instead of actually peeling the mashed potatoes. And so he will get the measuring cup, which I find funny, and he'll set it, you know, up there on the bar, and he'll do this, trying to get exactly 2 cups. Well, is he going to get exactly 2 cups? No. He's going to be a little bit over, which we're going to have soupy potatoes, right? Or he's going to be a little bit lower, and then we're going to have chunky potatoes. So the point is, well, how much is too, you know, high? How much is too low? So this is a perfect example. That's your h. What do we keep h around? Okay, is if you're measuring 2 cups, is going over by 1 cup making potatoes too much? Well, yeah, you got potato soup now, right? You know, and going 1 cup too low, that's too much. So this is where I'm trying to get to the point to you. What is the value of h? Well, how much can you stand? Well, a measuring cup, and I know you have stayed awake many nights wondering this, why the stripes on a 1 liter measuring cup are about 1 millimeter apart. I have a 1 liter measuring cup, and this is a right circular cylinder with a radius of 6 centimeters. What I want to do is this volume, okay, and this stuff I'm giving to you, this formula, the volume of the liquid that I put into this measuring cup is a function of the level. Now this is a different h, this is the height, you could say, of the cup. So it's a function of height. If I have the radius 6 centimeters, I just simply plug it in, and I have this formula for volume. So my height is what I'm trying to stay above 2 cups just a little bit, below 2 cups just a little bit. So what I could do, I could place this in an interval and, you know, ask myself, is too much error? Well, what I'm going to do is I'm going to say, well, how closely must we measure this height? Again, this is a different h, this is for height, out of a 1 liter of water, which is 1,000 cubic centimeters, which is no more than 1% error. I'm saying if I have a 1% error on potatoes, big deal, okay? And that's all this is saying, which is about 10 meters. So what I want to do is I want to hold that volume function, okay? Remember we said, well, we put that in terms of the height of the measuring cup. Am I a little over? Am I a little under? And I want to satisfy, this is my perfect world. You know, I would like to measure out, say, exactly 1 liter of water. Well, that ain't going to happen. I mean, you're not going to get it exactly. So what I do is I put it in an inequality and say, well, as long as I'm within plus or minus 1%, and hopefully you remember with inequalities, that's what I'm going to do, is I'm going to have a plus and minus here. And so this is my error. This piece right here is actually what we call our limit. That's we live in a perfect world. That's what I want. This value right here, I don't want to get too crazy with you, but most of the time you'll see this, and some of you that had this in high school have seen this formula. It's called epsilon, which I like this letter because you think of it, it looks like an E, that's your error. That's saying this is how much error I can stand. Take this inequality and I plug in my volume formula. And this is what you saw me do. I found this with the radius was 6. So 6, do this piece, the plus or minus. So this is all algebra that I've done so far that hopefully you remember when you have absolute values, you do the plus and minus. And now you solve for this in the middle. This in the middle says this is what I keep my height within. So if I solve, then the first thing I would do is add 1,000 to all 3 pieces because I'm canceling that out. And then I would divide all 3 pieces by 36 pi to put this in terms of h. Well, in our real world, we have no clue what these numbers mean. My calculator, and I get actual values to decimal places. So what I do is I round up the lower one to bring it up just a little bit. The height that's a little over, I round it down. So this even gives me a little bit better. You know, it gives me 1/10 of an error here. And what this actually means is we should hold the interval, this 8.9 minus 8.8. In other words, the height. If I hold it within this interval, this gives me 1% accuracy, which is, of course, fine in cooking. So again, all that's saying is you're trying to hit this point right here, okay? In our example, it was 1,000 cubic centimeters. That's what you want. That's my measuring cup. I'm making a big batch of potatoes. So I know I live in an imperfect world, and I cannot get that. So how far above and how far below this distance here is what's actually called that epsilon, or is called our error. And that's all a limit is, where this is our limit. We want to stay within some error. How close can we get to it? A lot of times it's gonna depend on your measuring tool. You know, if you're measuring something and you can only measure in feet, you can't even go down to inches, well, guess what? Your error is not going to be very small, of course. And then also it depends on, a lot of times out in the real world, your boss is going to say something like this, well, I want no more than 1% error. And so hopefully this, I know a lot of this stuff is very vague in this class, but this gives you an idea what a limit is the value we want to reach. The value of our function that we get really, really close to. It just so happens our functions that we've been doing are slope functions, that f of x plus h. So we're trying to get the value of, we're letting our h value go to 0. So this whole idea was used to define the derivative. When you see something like this that says the limit as x approaches c of f of x, what that means is I have some function, I have some value c here, and I'm trying to get the value of that function right there. And you say, there he is, and you say, well, that's stupid. I'll just plug that value into my calculator and I can get that value. Well, again, we don't live in a perfect world. You cannot get that exact value. You just can't. Okay? You can get close to it. Well, how close? Coming from either side, you can get within the interval, which is what we did with the measuring cup. We kept an interval, and we said that's close enough. And that's the whole shebang of the idea of a limit. Justin?
Is there a limit theorem for this in terms of like?
Yes, but we don't get, because
Interval.
I was going to say, you probably remember this whole deal. That slam. We're not going to do that in this class. Which if you recognize this, those of you that had this in high school, that was the measuring cup formula. You know, it's just, I didn't write it that way because I didn't want to scare people, but that was the volume formula. That was my limit, and that was my error.
Never had that.
Y'all didn't do this in high school? Did you?
They focus more on like the theory, the notes, and like what to.
I was going to say, y'all probably moved straight to shortcuts.
Yeah.
No,
Yeah.
we had, well, I had a piecewise function.
You did? Okay.
They basically made like, they gave us like mostly parenting and solving, and that's it.
You know of them in here.
Too bad.
Too bad. All right, so again, all this says is a number is approaching a function, okay? So in other words, the value. My f of x, think of my y. As x is approaching a particular number, what is my y close to? You know, as close as I want to get it to. All right, so if I have this function, y equals x plus 2, is y continuous at x equals 2? Yes or no? How do you know?
Because they're
It's a line. I mean, that's the easiest answer. Right? But if you want to be really mathematical, is you say because the limit and the value of the function is the same. So I've kind of already answered this for you. When you see something that says the limit as x approaches 2, you just simply plug the case. And so what you're looking at is, you know, as you said, it's a line. But if I wanted to get close to it from either side, and of course we can make these even smaller, 0.0001, then I could say, well, eventually I'm getting really close to this value of 4. That's what that piece is saying. This piece is just saying, if I look at x equals 2, which I guess is somewhere over here, then what's the value of my function? And that's all that's saying, is if there's not a hole in the function, there's no jump, then it is actually. All right, how about this one? Is y continuous for that function at x equals 2? No.
Yeah, no.
No.
As soon as it's 0, that's fine.
0, 0.
Jump to 2.
L'Hopital's remember that, huh? All right, stop scaring my students off again. All right, so in other words, hopefully you look at that and you say, well, no, I can't plug in 2 because if you plug in 2, you divide by 0. All right, so looking at this, what do you think that would be? What? No, a number. That is true, though.
4.
Okay, somebody said 4. How'd you get 4?
Tricks.
What's your trick?
You take, well, but I don't want to go ahead.
Tell me.
You take the direct, since that one's.
No, don't tell me that way.
Okay, you
Can-
have to.
Factor the top.
Factor the top and then the
That
bottom.
cancels. Now you plug in 2 right now. So in other words, what this actually is, so if you notice, let me rewrite that again so you can see it here. So I factored the top into x plus 2, x minus 2. And so as you can see, that cancels, and it's like, oh, that's just a line is all it is. But remember when you did domains, they told you to go back every single step. You can't plug in the value of 2, so at 2 here, there's a big hole. So this function, which you already said here, is not continuous at that value. It's jumping over because I'd be dividing by 0. But the limit, and this is the big key, a limit does not care what's happening at that point. It could care less. It cares what's happening near it. As I'm getting near, closer and closer and closer to 2, the value of my function is getting closer and closer, and eventually it's getting to 4. Okay, and that's what the limit is saying. The difference between the value of the function, if I just flat out asked you, well, what's f of 2? You would say it does not exist because you cannot plug in a 2 there. But if I asked you the limit then, either one, the easiest way is look to see if you can factor something to get this limit. Or in this class, this is, you know, I hate to say it like that, but in this class, we don't even do this stuff, factoring. What we do is we pick values very close, or very small, I should say, to the value we're trying to get to. All right, so you mentioned piecewise functions. So here, this says, I already know what that looks like. This says that I have a line with a hole in it at 2. This says that I've also defined, well, if x equals 2, then I'm going to color in a circle and I'm going to put a 6 there. Is this function continuous at x equals 2? continuous. How about this one?
No, because it's
Okay, so it's not continuous, so what's the limit?
D and E. What?
D and E.
You showed it. It's a does not.
N-E. Is what I thought you said D and E like this was multiple choice. All right, so actually if you look at this and you plug in 2, you're going to see that, of course, this is, and what you also mentioned was with asymptotes, we have a vertical asymptote here. If my x value is getting really, really close, and this is, again, something we're not going to get a lot into in here. If I'm getting really, really close to 2, on this side of the function, what's my function doing? It's heading to infinity. So technically, this limit, if I'm coming from this side, is going to infinity. This side is heading decreasing, going to minus infinity. Again, in here, this would be more, let me just write that, but this would be more like you just said it, that this is just increasing without bounds, you might say. This is decreasing without bound, okay? All right, so find the exact value of a derivative using the limit definition. This would be like something that you might have to do on the test. That's why I said this isn't, so far out there. This is new stuff, but this is still what you guys are doing. So I give you a function, and I say find the derivative using the limit. So this is the limit definition, and finding it at 0.1 seconds. So what I'm going to do is I'm going to plug in 0.1 plus h, so this is my x plus h minus my f of x all over h. Okay, so this should be something you should be able to work right now. Okay, if you can't, then we just need to practice, and we're going to do, some more of that. So what I'm going to do is I'm going to calculate this, and then of course simplify so I can finally let my h. And then step 2 is what I'm doing, where I let this go to 0, which is finding the limiting value. That's actually finding my limit from this first expression. So again, it's 2 pieces. It's one, plugging in this information. This is your x value, okay, that's given to you. And then I'm going to plug in, I'm going to go through and try to make this look a little bit better by plugging it into my function here. All right, so again, this seems to be the hardest part for every calculus class I teach. It doesn't matter, which calculus it is remember, and we're going to do this in 2 steps. I'm going to do this side, and then I'm going to come back and do this side. So all this says is everywhere you see an x, every single place you see an x, plug that in. So that's what I did. Negative 16, all that junk squared because it's x squared. Plus 20x, this is my x, and then plus 7. Okay, so we did this, a few weeks back, some of the first group work in the course, so it's been a while. And this was a lot of the questions. Well, how do I know to square that? Because your variable's squared. Okay, so all you're doing is you're just simply taking where you see an x and plugging in the 0.1 plus h. All right, now you have something that you can do algebra with. Don't leave me. Algebra now. And sorry this jumps so much like this, but the algebra meaning that I'm just going to FOIL this. Okay, so you remember all that good stuff. In other words, I'm just doing 0.1 plus h times 0.1 plus h. So that's that piece right there. Okay, so that's all I did there. Here I went ahead and distributed this. Okay, so that's all I've done so far. And I know some of y'all are writing, these slides are online. I mean, you can write. Like, throw your pencil down when I say that. I may just go too fast for you to keep up with the writing. All right, and so now all I did was distribute this negative 16. So again, all I'm doing is algebra. I'm just sitting there making this look better by distributing all that out. And finally, I just go through here and I say, well, are there things, here's some h's here that I can collect. Here's some actual values that I can collect to just finally, again, all of this is just pure algebra. No calculus involved. So remember, this is just the one side of the numerator. I still have to do the other side of the numerator. So now what I'm going to do is everywhere I see an x, I'm going to plug in this 0.1. So I do. Okay, so negative 16x squared, 0.1 squared, plus 20 times x, 0.1. And if this is like, man, this is way too much going on, this would be a good example to go over for the test, okay, to make sure you understand these steps. And so now I just simply, all I've done is just multiplied things out, okay, I just squared that, multiplied this out, and then I get an actual value. Now, I want you to notice that this value equals this value. If your numbers do not equal, you did something wrong, because the numbers will always cancel. You will always be left with only things in terms of h in your numerator. If you didn't, something went wrong, meaning that you need to go back, and look at this, or go back and look at this, which that's good to know because it's right track. So as you can see here, why I say that cancels, we're going to have 8.84 minus 8.84. Because the whole point of all of this is I need to get this out of the denominator, and I can do it now by simply factoring. So I canceled that piece out. Now I'm going to, so I factor down an h here. Now I can simply cancel, and I'm left with this negative 16h plus 16.8. The second step says take my results, and my results actually is a derivative. I mean, this is the derivative. And take as h goes to 0, meaning h gets really, 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 really small, well, why not just plug in 0? And you might say, well, why didn't we plug in 0, 30 pages ago? Well, we couldn't because we can't divide by 0. So that's what we do. We get to a point where we can find, and then I actually get my limiting value. Again, if you did this, meaning with a table, and you just simply used really, really small values of h, you would see that you would get. So that's what I did here, is I said, well, I don't want to go through all that junk. I just want to pick, small values. And these small values mean what? How much error can I have? If this is good enough, then I'm done, okay? If I can, then I go through my steps to say, well, this is this value. If I went even smaller, what you would end up seeing is this would start getting more zeros out here. Okay, and so eventually you're going to this value of 6. Again, you could call the limiting value. All right, so, and again, in our example, that 16.8 is the slope, right? I mean, it's the rate of change of this ball. All right, here is going to be something different. I don't give you the value of x, because that's kind of the whole point of this, is the first one I said at time 0.1. Now I say, well, do it again for 0.3. How many of you want to go through all those steps again and do this again for another number and another number? I don't. I would like to have one function, and that's what we want to do, have a function that I can plug in any number I want. So, and this gets really just messy looking, everywhere I see an x, notice I plugged in x plus h. Okay, and it's just a lot of algebra here. I mean, things can get lost. And then everywhere I see an x, well, that's easy. I plug in x, meaning it's just my same function. Be sure you get these parentheses here, because this negative is going to end up making, something cancel out. So I have this big old, definitely something you should take time and go through. I foiled this. That's right there. I distributed this out. That's that piece right there. And then I said, well, let's just go ahead and distribute out this negative sign. So that's all I did here. So I got positive, negative, and negative. Okay, again, this is all just pure algebra. It's just a big, ugly mess. And now I'm going to multiply this, distribute it out, and you're going to see a lot of things are going to start to cancel. If I look right here, negative 16x squared and 16x squared canceled. And then the next thing I do is I do this one, which is my minus 32xh. Then I get minus 16 h squared. Here is my 20h. I'm sorry, there's my 20h. And as you can see, everything else canceled. Notice what I told you earlier. I said all the numbers will cancel. Well, if we had a value of x, wouldn't those be numbers? So a better way to say it might be you should have nothing left up here but things with h's, because we're going to end up factoring them out. If something ended up here, I don't know, like let's say you forgot to do that and that was a plus and you ended up with plus 14, then you need to go back here. And I mean, this is just something good to know because you know not to continue anymore because you're not going to get the right answer. And so now, factor out my h, because that's the sole reason why. I hope you know why do I want to do that? Because I cannot plug in a 0 right there. That's why I had to go through all this junk to get to a point. Oh, now I can actually plug in a 0. And now as I take a 0 and plug in a 0, I actually have a function now that I can take and plug in any value, okay, for my x into this function. And this is what we're getting to in this course, where we're no longer just coming up with an answer, a numeric answer here. We're actually coming up with the derivative function. Our numeric answer was the derivative, the slope. Makes sense, right? A number's the slope. Now we're saying, well, I could find the slope at a particular point. I could find the instantaneous rate of change of what's going on at 1 second by plugging 1 in there. And again, this is how it's written. My derivative function, f prime of x, equals this. So now let's interpret this. Say if I want to know the speed of the ball at time, well, this simply means that I'm just plugging in. My x is my time. I should say I'm plugging in 0, and so I get 20 feet per second. If I want to know the speed of the ball at time 0.1 second, I just simply plug in 0.1 here. And guess what? I got that same answer. So the nice part of this is if I would have only shown you that first way and I told you to find this and find this, you would have had to do all those steps twice. But now when I say, no, why don't you just get a function so you can put any value in here, it makes it nicer and of course faster because now you just have a function you can get the speed of this ball at. All right, so again, I believe I was going to say this is the last one here. I got more slides. I know you're excited. When we say something is continuous, say at a particular value, this x equals a means your a is 3, my a is 4, yours is 2. We could have different values. There's no hole, okay, meaning an open circle there. If there is a hole there, it's not continuous, but the limit could still exist, like in our pictures as I'm getting close to a particular value. If there is a jump in the function, meaning that, and this is more of the, I'm jumping from here to here, then we say the limit actually does not exist. And then finally, the definition of continuity is the easiest thing to say is if the limit exists and the value exists and they're the same, then it's continuous at that point. Okay, and as I mentioned, this is kind of a, I don't know what they call it, focus on theory or something. If you want, if you're really interested in this and you want to read more, and I know you do, right? That was a joke.